Hey there everybody, welcome back to another Chem Complete lecture. And in today's lecture we are going to continue our discussion about enolates. And before we get ready to talk about condensation reactions, I want to take a look at how we can control enolate formation through various chemical and environmental conditions that we can subject the aldehydes or ketones to as we are getting ready to form an enolate. So, enolate control through conditions is the topic for today, and that's coming up on the channel right now. Alright, before we get started, remember to hit that like button if you enjoy the content that we give here. And down in the description box, you can find links to our website, the guides that we sell to help you through organic chemistry. They're very, very affordable, and it helps support the channel. So let's get started. Now, if you did not see the last lecture, I would strongly encourage you to go back and take a look at the initial lecture on enolate formation. So, since we have already discussed what enolates are and how we form them, I wanted to talk for a moment about how we can control the formation of different enolates when more than one possibility may be present. So, to start, when we are talking about ketones specifically, this is usually where this will arise as a potential problem. Now, it's not usually going to be with aldehydes because the aldehydic proton takes up one of the two sides, and that is not an alpha position that is deprotonatable. And esters are in the same sort of situation where that OR group, whatever it might be, is not going to be in a deprotonatable state. So only the other alpha portion of that ester will be removable. However, when we get to ketones, ketones have two R groups, and unless there is one specific R group where there are no hydrogens on the alpha, which is possible if you have something like an aromatic ring or a T-butyl group, you will end up potentially having more than one possibility as far as where you can deprotonate from. Now, with symmetrical ketones, you're only going to have one enolate. It is not going to matter. So if, for instance, we were to take a look at acetone, which is the example we used throughout the last lecture, acetone is symmetrical. Now, when I say symmetrical, I'm talking about the alpha position that I find to the left and to the right of the carbonyl is identical. And so therefore, whether my base material came in and deprotonated a hydrogen from this carbon on the left or this alpha carbon on the right, it doesn't really matter because the same result is going to ensue, which is that I will get a CH2 group and then I'll have the carbonyl, right? So that will be the enolate that forms there. And no matter which side I pick from, that enolate in three-dimensional space is going to be symmetrical, right? There's not going to be a big difference between them. They would be identical to one another. So the issue is really going to come up or arise when an asymmetrical ketone is present. And that's where we run into the need to control which result is going to be present. Okay, so keeping the example still relatively simple, let's go ahead and use 2-butanone, because now I will have an ethyl group on the one side and I will have a methyl group on the other, right? So this is different than the acetone example because the CH3 group on the left is not the same thing on the right. I now have an ethyl group. And so I really could create two potential enolates, right? The first one being that I could target that group that's over on the left, and I could keep the ethyl group intact here. And then I could also take the opposite route and I could say that this will be the alpha carbon, and so the methyl group on the left is what will stay intact. And then I get a CH enolate right here with the methyl group, right? So these are two different enolates at this point, and they would make very different products if I sent them out into some sort of a condensation reaction and I was looking at the result. And so the question is, how, and really can, I control which one of these I get? And the answer is yes, you can control it. Now, in certain situations, you may end up with a mixture. It's not 100% guarantee that one method is going to completely selectively control over the other, but we do have pretty good conditions that we can set up and pretty good chemical choices that we can use here in order to promote the formation of one over the other. But before I talk about that, I want to label these because they are known as two different types. This is the kinetic enolate. Okay, we'll talk about why in just a second. And then this one down here would be known as the thermodynamic enolate. Okay. And the term thermodynamic is stemming from the fact that the energy of this enolate is going to be lower and more stable than that of the enolate up top, the kinetic enolate. Okay, so the kinetic enolate, you can see from the note here, is the less sterically hindered alpha position, and it will always form first, right? So one of the main answers that students will always throw out when they're in undergraduate organic is sterics, right? And it's for good reason, because sterics explains a lot of behavior, whether we're looking at SN2 behavior or whether we're looking at whether a certain reaction will occur at one site versus another. Steric hindrance and steric strain is a very prevalent feature or answer in organic chemistry when we are considering reactivity, right? So if we take a look, an ethyl group is bulkier than a methyl group. And so it makes sense that this side of the ketone is going to be less sterically hindered, right? There's going to be less sterics that are associated with this side of the ketone compared to this side, where I would have more sterics because the group is larger. And so it does turn out that you will always form the kinetic enolate first, okay? However, the kinetic enolate is not the most stable enolate of the two. It is simply the path of least resistance, if you will. In other words, when the base is coming in and it's looking for a quick fix, or it needs to abstract a proton as quickly as possible, it is going to go for or attack the less sterically hindered site. It's only natural for it to do that. However, what we want to consider is the fact that the thermodynamic product is really the favored product if possible. And the reason for that is really going to be, if you take a look at the other resonance form of the thermodynamic product. So let's draw that down here. Okay. So the alternate resonance form for this thermodynamic product, we would have the C with the O minus, and that would really be the major resonance form, right? But then you have a carbon-carbon double bond property down here with this carbon, and this carbon here would have a hydrogen, and then it would have the CH3 group. Now the reason that this is called the thermodynamic or the more stable product is because if I look at a carbon-carbon double bond, one of the things that helps to support carbon-carbon double bonds is hyperconjugation. Okay, and so hyperconjugation is going to be looking at the donating effects or the slight donating effects from any CH hydrocarbon groups surrounding the p orbitals associated with the carbon-carbon double bond here. And so if I had the alternative where I would say I've got CH2 over here double bonded to the carbon that has this O minus, right? So this would basically be the kinetic product in its other resonance format. Well, if I take a look, this carbon-carbon double bond only has one hydrocarbon group that could potentially help donate through hyperconjugation. whereas this one is going to have 2 R groups or CH groups that could potentially help donate through hyperconjugative processes. And so the thermodynamic product, or the thermodynamic enolate, is really the favored or the more stable enolate because of this factor, okay? But it's not the first one to form. The kinetic is going to be the first one to form. And so this is really where we start to get into the heart of the discussion regarding controlling the enolate and the conditions that we're going to be setting up, okay? So the kinetic enolate is less sterically hindered at the alpha position, and it will always be the first one to form in comparison to the thermodynamic. So the thermodynamic enolate is more substituted and is a more stable enolate, energetically speaking, because of that hyperconjugation contribution. So one more time, I'm going to draw this out here. The kinetic enolate is going to be the one that is less sterically hindered, meaning we get quick access to it. Think about kinetics, movement, quick, rapid, right? We can make this far faster than we can the other because it's not as sterically hindered in that position. However, if we want to take a look at the overall energetics of an enolate long term, then the opposite would be true, and we would want to start favoring the thermodynamic, right, setup, which would look like this. And again, it's that presence of the additional R groups. And when I say R generally means a hydrocarbon group, right? Rest of the molecule in organic chemistry. That's what the R stands for. So the thermodynamic is more stable. Okay, thermodynamic enolates take time to form, and this is the key. They require reversibility in their conditions, and that makes sense because if I'm going to form the kinetic enolate first under all conditions, then I have to have some reversibility in that in order to obtain the thermodynamic enolate. I'm going to have to be able to kind of backpedal or backtrack to the opposite form and then allow it to proceed forward to the thermodynamic enolate instead of the kinetic enolate. So having reversibility in your conditions is key here. Now, how do we get reversible conditions versus irreversible conditions, meaning the kinetic enolate forms and then we lock that kinetic enolate in. It's not allowed to go back and be reversed into the thermodynamic enolate, okay? So for kinetic control, the use of a stronger base is important, okay? And cold temps are also important. So cold temperature is very important here. And that does 2 things. The use of the strong base, okay? If you use LDA, and LDA is lithium I can't remember if it's isopropyl or isobutyl amide, okay? So it's a very, very strong base, and it is so strong that if you take a look at the opposite end of it, when it actually has picked up the proton, it's got a pKa of somewhere around 36, and that is very, very strong. So the reason that I bring that up is that it's a very, very strong base, okay? The reason that I bring that up is that if we take a look at this, okay, if you have the... Hold on a second here. Sorry about that. If you've got the ketone, and then you expose it to LDA, this ketone is going to have a pKa of approximately 19, somewhere in there, maybe 20. Okay, and then as you go forward and you use LDA, the LDA will come and pick up the hydrogen, right, from the kinetic area, and you will end up with your enolate. And along with that enolate, you're going to get the conjugate acid for the LDA. And the conjugate acid for the LDA, or the LDA that's protonated, is going to have a pKa of 36. So the reason that I'm bringing this up here is that if we take a look at pKa, pKa tells us how strong an acid is. And if your pKa has a vast difference, okay, between the two sides of the reaction, it will always favor the weaker side, okay? And the reason for that is that if I take a look at this, a pKa of 19 and a pKa of 36, you want to look at the general difference between those. And when I say that, what I mean is if we've got 19 and 36, 36 minus 19 is 17, and so the order of magnitude in difference between their acidity is 10 to the 17th. So what that states is that every single time that the LDAH attempts to go back this way and make it reversible, 10 to the 17th of these acetone, well, it's not acetone, of these two butanone molecules will come over into this form right here. So basically what we're saying is no, this cannot happen to any effective degree because there's going to be such an overwhelming amount of movement this way on the magnitude of 10 to the 17th that the return volley is going to be insignificant or not applicable here. And so what we do is we essentially create the kinetic enolate, and then we make it a unidirectional reaction because the difference in the pKa is so large here. Okay, the colder temperatures, and usually you're going to see something like along the lines of minus 78, because that is, if I'm not mistaken, a dry ice bath that you would be able to create for typical organic chemistry conditions. And when you have that, the robbing of the thermal energy from the system, along with the vast difference in acidity, both of those factors come together to really shut down the potential for reversibility, which is what you have to do if you want to lock in your kinetic enolate. Otherwise, if you have reversible conditions, you're going to be headed back or inching back towards that possibility of a thermodynamic enolate, which is, again, where it wants to reside for stability purposes. Okay, so then how do we end up promoting thermodynamic enolates? Well, the use of hydroxide, which is in this case a weaker base, okay, and mild to warm temperature. So even like around room temperature is usually sufficient in order to start promoting a thermodynamic enolate. But if you make it very cold, then you're going to start forming the kinetic and kind of locking it in there. Okay, so again, the same pKa argument is in play here. So I've got roughly 19, right, for the 2-butanone that I am working with. And then if I take a look with hydroxide, well, the hydroxide is going to become H2O, right? If this OH pulls off a hydrogen from the kinetic position at first, it becomes H2O. Well, the pKa for H2O is, if I'm not mistaken, it's like 15.7 or something around there. So while there's still a difference here, okay, it is not a vast difference like the 36 and 19. And if anything, this is technically stronger, which means that it will fire more back in this direction, which is going to allow the thermodynamic enolate to slowly establish itself, right? Because the kinetic initially forms, this gets sent over, and it kind of pushes some of it back here, because this, the pKa being lower, means that this is a more effective acid than the 2-butanone is. And so it can very easily go back. It's not a big issue there. Okay, so that will promote the thermodynamics. So just one more time as sort of an oversight here. Sorry, CH2 for the kinetic at first, right? One more time for the overall thing. Kinetic is going to be the use of a stronger base, specifically LDA is what we usually come across here in this part of the course, with colder temperatures. That will lock in the kinetic or the less sterically hindered enolate. Thermodynamic conditions, which includes reversibility, will use the weaker of the two bases, which in this case is hydroxide. Sometimes it's weird to talk about hydroxide as a weak base, but it's all relative, as we know in organic chemistry. Okay, and then some mild to warm temperatures. And the warmer they are, the more you are setting up the potential for reversibility in the reaction there. Anyway, I'm going to cut it off there. Again, shout out to chemcomplete.com. If you want some additional help, please head over there and check out the guides and the resources that the channel has. It's a great way to support the channel. Other than that, like, comment, subscribe. I'll try to get back to you as soon as I possibly can. And I really appreciate you taking the time to learn with me today. I will see you guys for the next lecture.